Hello everyone, welcome to my lecture today. So for this lecture, I will give similar topics of the probabilities of some classical discrete random variable here. So in this lecture, I want to talk about one more distribution. This is a hypergeometric distribution. So in our previous videos, we already talked about the Bernoulli trios, binomial distribution, geometric distribution, negative binomial distribution. So here, this hypergeometric distribution is also a distribution related to our previous examples. So here, the first thing is let me give a definition of this distribution. So assume here we have n objects, a set of n objects, and in these objects we contains k of the objects is denoted as a success. And the others, so in other words, is n minus k objects is be labeled as failures. So you can see this one is a little similar with the binomial, right? So it's like we have two kind of group. One is succeed, one is fails. And here what we want to do is we want to select a sample of number small n objects. And then, so here, this select, of course, is randomly, and also this without replacement. So when we select one of the items, we will put this apart and didn't return this to our whole capital N objects, and then we will select the second one. So now, based on this statement, then of course, this k and small n should be smaller or equal to our capital N. And in this one, we will define a random variable. So generally here, we can denote this by x is equal to the number of succeed items in our sample. So this we call it a hypergeometric random variable. And of course, similar with our previous videos, I want to give the PMF, probability mass function of this random variable. So the PMF of this hypergeometric random variable is look like this. So in the numerator, there is two combinations times each other. So the first one is k and x. So that means here x is a number of succeed in our sample, right? So the first combination means in this k items, which is succeed, we select x from them. And then the second combination is in this sample we have small n objects. So that means except these x items, the others, which means small n minus x, the others is a choose from the failures one. So because the number of failures in our whole capital N objects is capital N minus k. So that means the second combination is select small n minus x objects from the failures part. And then what's the denominator of this one? So denominator is divided here. Denominator is also a combination. So here this means we just randomly select the small n items from the capital N objects. So here what we know from this one, you can see actually this one is just how we can compute the probability of select small numbers samples with x of them is succeed. So this one is just a way we can compute this probability. Okay, and here, so for our x, small x, there is some requirement, right? Because this x is, what's the meaning? It means how many succeed items in our whole sample. So here for the sample, of course, this x should be smaller than our sample size, small n. And also, this x is about succeed. So no matter how many items we select from this sample, how many items we will select from the whole population. So here, these succeed items should smaller than the total number of success objects, right? So that means this x should also smaller than capital K. Okay, so this is the upper limited for or upper range of our x. And then for the lower range, what this means. So of course the smallest number is 0. It means in our sample there is no items of success. And then the other thing is they can also be larger than n, small n plus capital K minus capital N. So what this means? This means for our objects of the sample plus the whole numbers of the seed minus our capital N. So if you think this is a little confusing, then maybe we can rewrite this. So this is what means small n minus capital N minus K. So what this means, so capital N minus K, this is a number of items for our future. And then, so small n minus is capital F is, so for our samples, the number of, in these samples, the number of succeed should smaller than the number of the success in the whole population. And the number of the failure in our sample should also smaller than the number of the failure in our whole population, right? So this term actually is to make sure our failure in the sample should smaller than the whole numbers of the failure. Okay, so this is what is our definition of this hypergeometric random variable. So after we have this one, so similar with our previous lecture, I want to give two important terminology or property of our random variable. So they are the mean and variance. So if you assume the x is a hypergeometric random variable with parameters capital K, capital N, and small n, then the mean, or say the expected value of our random variable is n times p, and the variance denoted by sigma square is equal n times p times 1 minus p times number capital N minus n divided by capital N minus 1. So careful here, this is not a combination, this is just a division here, okay? So here, what's the meaning for our p? So p is a proportion of our success in the size of the capital N objects. So this is the meaning of our p. So here we write this p, it just make sure the formula for our mean and variance is looks simple. Otherwise, it will be much longer than these two equations. Okay, and here also by this equation, maybe now you can have idea why we say this is a hypergeometric random variable. So if you compare this with our mean and variance of the binomial distribution, you can see that kind of have some, commons, right? Like the equation of the mean and the formula for our variance. So that is also why we introduce the hypergeometric random variable here, just follows all the distribution related to our binomial distribution. Okay, so next thing, after I give the definition and mean variance and PMF of our hypergeometric random variable, let me give one example of this. So here, let's look at this example. Assume here we have a lottery game, and this means we will draw 6 numbers from the total of 42 numbers without replacement. So then the prize are awarded to players who match 4 or maybe 5 or maybe 6 of their numbers to one draw, so which is decided maybe by the organizers. Then what is the probability of matching exactly 4 numbers? And then ask us what is the mean and variance of the matching numbers. Okay, so this is an example. So then the first thing is, let us look at this one. So here, in this one, what player will do, they will select 6 numbers from total of 42 numbers. Although actually the 42 numbers are different with each other. However, here in this one, there are different kinds of property of this number we draw. Yes, they have the matching or not matching. So if the number we select is matching some given number, then this kind of means we succeed in this selection. And then if this our number is not matching a given number, then that means it's a failure. So that's why here for this example is a hypergeometric distribution. So here let us first define what is our hypergeometric random variable. So here let us define our random variable x be the number of matching numbers when one player get their drawn. So in this situation, in the question, they ask us what is the probability of the matching exactly 4 numbers. So in other words, what this question asks, the question is asked about what is the probability x is equal 4. So this is what this probability and how we can translate this question to a probability language. So here if we do this, then what we can do, now we can use the PMF of our hypergeometric random variable. So here this is our formula for the PMF of this is a PMF of our hypergeometric random variable. Okay, and then the next thing what we need to do is we need to find all of the value of our k, capital N, small n, and x. So here in this question, the first thing is what is our x? This x is actually the value of our PMF, right? So that means here the small x is 4 because we try to find the PMF at point 4. And then what is a capital N? So here capital N is how many objects in total. So in the question, because they say we select 6 numbers from 42 objects or numbers, so that means for our capital N, this is 42. And then the next thing is what is our capital K? So here for the capital K, this is what means succeed. So or what means success. So here when a number is success, this means it's matching for a number selected by the organizer. So here how many numbers the organizer will select? Of course is 6. So that means our capital K is also 6. And then what is our small x? So here what is our small n? So here small n is how many objects we want to select to group as a sample. So here is the player, how many numbers player will select. Of course they will select 6 numbers. So that's why here the small n is also equal to 6. So in this question, I hope you should careful about the value of k and the value of small n. Although they are both as a number 6, however, the meaning of them is a little different. Capital K 6 is about the organizer will select 6 number. And small n equals 6 because the player, all of the player will select 6 number. So although they are both 6, but they have different meaning. Okay, so then after we have all of these values of small x, capital N, capital K, and small n, the next thing is we just need to plug in all of these numbers into our formula of PMF for a hypergeometric random variable. So when you put in all of the numbers into our formula, we will get this equation. And then the next thing is use our calculator and the definition of combination to compute all of these 3 combinations and then compute the multiplication and division. So then I just give you the final answer. So the final answer of this is 0.0018. Okay, so this is what we have for this compute this probability. And then the next thing is in our part, other part, we also have what is a mean or the mu expected value of our question. So this is by the formula is n times p. So here n is small n is how many numbers every player or will select, or in other words, what is the size of our sample. So answer is 6. And p is what? P is in total how many succeed in our population, or say in our capital N's object. So here is 6/42. So here this 6 is for each of the player, and this 6 is for our organizers. So I hope you can find the difference of these two.